The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, so last day, let's get down to business. Last day we started studying crystallography, and we were looking at ordered solids, and we recognized that crystal structure is the sum of the combination of the Bravais lattice, which is the way that points are identified in space, plus the basis. And we saw that we could put a variety of elements at the corners of the Bravais lattice, and this is taken from the archival notes where we see the simple single atoms at the various lattice points, and we recognized last day that we could put clusters of atoms and so on, and even proteins will crystallize in this form. And actually, to make the point, about 5 years ago, a group of students came to my office after the final exam, and recognizing that I drink Fresca during the lectures, they came to me with this body-centered Fresca unit cell. So this just makes the point that you can put anything at the lattice point. So there it is. And what we did last day is, here's the point. This is me at a conference in Copenhagen. This is outside the Admiral Hotel. And just to show you, I'm always thinking about 3091. I came outside, and this is a colleague of mine from France, Marcel Gonescard. How do we know she's French? She's got a cigarette, and she's a scientist. She's a woman, and she's smoking, and it's fantastic. And she's a great gal. And anyways, so there we are out in front of the Admiral Hotel, and I noticed these cannonballs. And what do you notice about the cannonballs? They are sitting in one of the Bravais lattices. And so I couldn't resist and had my wife take this picture because I knew that this would come back to 3091. So here we are with the individual cubic lattices where we're going to focus. And we started looking at the properties of cubic lattices. And I started working through this table. And we got down to nearest neighbors and so on, and this relationship between the lattice constant and the radius. And I just wanted to show this last point here about packing density because it comes up in considerations of properties of elements. And so I wanted to go through the packing density calculation. And so the way we handle the packing density, remember we're looking at a unit cell here. This is the cube, that's the repeat unit, and it has a lattice constant of dimension A. And then depending on where we put atoms, and I want to show that we've got three different options here: simple cubic, body-centered cubic, and face-centered cubic. And the last line of that slide shows that the densest packing of atoms, this is hard spheres, the cannonballs, the densest packing is face-centered cubic. And I wanted to show the derivation of that, where if we face-centered cubic, where the atoms are big enough to touch, so we have 4 atoms at the corner touching on the face diagonal and then continuing through the cell, we want to get packing density as the ratio of the volume occupied by the atoms, and here we're modeling the atoms as hard spheres, divided by the volume of the cell itself. And so that's pretty straightforward calculation that we're modeling the atoms as hard spheres. And we saw last day that if we take the fraction of the atom, 8 times an eighth and 6 times a half, we have 4 atom equivalents per unit cell, and each of these has a volume of 4/3 pi r cubed. And then if we divide that by a cubed, and then we know the relationship between a and r, this is 4r, and that's root 2a, so we can say root 2a equals 4r, and either eliminate a or eliminate r, we eventually end up with this dimensionless group, which is pi divided by 3 roots of 2, and that is 74%. And that's the densest packing. If you go through the same calculation for body-centered cubic, you'll find it's 68% packing, and for simple cubic, it's 52% packing. That's the highest density that you can have. So I urge you to spend some time. If you work the homework, you'll work your way through that chart. So now I wanted to take a few minutes and talk about crystallographic notation because we need to know this in order to describe various features of a cell. So I'm going to start with a Cartesian coordinate system. that obeys the right-hand rule. So we'll put down x, y, and z, and then we'll put up a unit cell here with edge A. So we have A on the x, y, and z coordinate, and we know that A equals B equals C. That's the unit vectors here. There's a little a here, a little b here, and a little c here. These are all equal to the lattice constant value A. And all of the angles are 90 degrees. This is what defines the cubic system. So I'm going to put several positions here. So here's the origin, and the origin we designate as 0, 0, 0. I'm going to put a position up here, A. And this, you just use the same notation as you'd use in mathematics, only crystallographers don't put parentheses around it. So what I'm really teaching is notation. You already know the math. So A up here is what? It's 0 units on the x-axis, it's 1 unit on the y-axis, and 1 unit on the z-axis. So that would make it 0, 1, 1. And I'm going to put a B out here. B is out 1 unit on the x-axis. It's 0 units on the y-axis, and it looks like it's up at about a half a unit on the z-axis. So that makes it 1, 0, and a half. And so now what I want to do is show you how we designate directions and planes. We use a slightly different notation from what you're used to in math. So this chart, which will be posted at the website, move the coordinate axes so the line passes through the origin, define a vector from the origin to the point on the line, and choose the smallest set of integers. So let's do a simple one here. Let's do from origin to B. So O to B. That's this vector here. So how would we do that one? Well, we're already at the origin, so that's trivial. O to B, so we're going from here out to here. And then what does it say? It says choose the smallest set of integers, no commas, clear fractions. So that's going to take us out to 1, 0, a half. But the crystallographers don't like fractions. You're supposed to clear the fractions. You clear the fractions by multiplying through. So make that 2, 0, 1. It's the same direction. See, if I came out 2 units here, I'd end up being 1 unit here. So it's the same direction. It really is the same direction. Don't put any commas and put brackets around it. So that's the 2, 0, 1 direction, which is OB. And I'm going to do a different one. Now I'm going to go this way, A to O. So let's look at that one, AO. And what happens on AO? Well, now I'm going to put the origin at A. I'm going to go to, let's see, I'm going to go 0 in the x-axis. I'm going to go -1 in the z-axis and -1 in the y-axis. So that gives me 0, -1, -1. But see, they don't use commas. And so this looks kind of goofy because you get these minus signs in here. So what the crystallographers do is they put the minus sign on top of the number. So this becomes 0, 1 with a macron over it. This is if you studied Latin, you know this thing is a macron, a line over a vowel. So 0, 1 bar, 1 bar, and that's the direction AO. So that's the macron acting as minus sign. So that's the AO direction. And then furthermore, we can designate families. This is just the 0, 1 bar, 1 bar. If you want to be a hipster with crystallography, you call this O. You say it's O 1 bar, 1 bar. But if you're a nice chemistry student, you'll say 0, -1, -1. No, we don't do that in 3091. O, 1 bar, 1 bar. Now suppose I wanted to describe all of the faces, every face. So what I could do is I could say I want the set of all face diagonals. Set of all face diagonals. Well, that's a face diagonal, but what I can do is, in a compact notation, I could write O, 1, 1, and use the caret. This is called the caret. So if I enclose in carets, this means the set of all O, 1, 1 type planes. And so what that means is I can unpack that and write O, 1, 1, O, 1, 1 bar, O, 1 bar 1, etc. And what I'll end up doing is describing the set of all face diagonals. So if I want to talk to you later when we're studying X-ray diffraction, I want to talk about face diagonals, I don't use that word. We're quantitative here at MIT. I say, look at the O11 planes. So you go face diagonals. That's the compact notation. If we want to look at all cell edges, what's the cell edge? Here's the cell edge. This is an edge here, isn't it? It's right on the edge of the cell. So it's 0 in the Y, 0 in the Z. It's 1 in the X. So the set of all cell edges would be 001. And you could write 100, that's okay too. Or you could write 010, that's okay. But if you want to be a hipster in crystallography, put the zeros out in front. So the set of 001 directions is all the cube edges. And then lastly, if we wanted to get all the diagonals, the diagonal that starts from here and goes up, we'll have all cell diagonals, all, if you want to call it body diagonals, not face diagonals, body diagonals. Body diagonals is 111. And the mathematics imitates reality. How many combinations are there here? I've got 0, 1, and I've got minus 1. So I got 001, 001 bar, 010, 01 bar, 01 bar. Oh, there's 6. And how many edges are there? 6. Mathematics imitating reality. What a concept. That's great. Okay. So that's good. Now we want to look at planes. Let's look at planes. Now, planes are a little bit different. This is basically what you know from math with a little bit of notation, right? Basically the same thing. Planes quite different. So let's go to the planes. So you know the equation of a plane. It's x over a plus y over b plus z over c equals 1. And a, b, and c are the intercepts at the x, y, and z axes. Well, in order to make this notation compatible to what we have here for lines, a British mineralogist by the name of William Hallowes Miller in 1839 said, let's define h, k, and l as the reciprocals of these intercepts. And now we'll write the equation of a plane as hx plus ky plus lz equals 1. And we'll use those values of h, k, and l as the indicators of a plane. So here's an example. So again, I've got the right-handed rule coordinates, and here's a plane, and you can see that it cuts the x-axis at A, it cuts the y-axis at B, and it's parallel to the z-axis. So if we were just to use the old mathematics notation and put the A, B, and C, you'd have 1/2 here, you'd have 1 here, and you'd have infinity here, and that looks goofy. So instead, what we want to do is use the Miller indices, which are the reciprocals. So now the reciprocal of 1/2 is 2, the reciprocal of 1 trivially is 1, and the reciprocal of infinity is 0. And so now you have something that makes sense, and you put no commas in between, and you put the whole thing in parentheses. So that's the 210 plane. And there's a really cool property here, and that is using this same formulation I just showed you for directions, the 210 direction, see 210 with square brackets, that's a direction. 210 with parentheses is a plane. The 210 direction is perpendicular to the 210 plane. And that's one of the advantages of using Miller indices notation with the classical notation for a direction. Here's another one. This is 010, right? This is the x, y, and the z, so this cuts at 1, 010. This is 020. And 010 directions perpendicular to 010 plane, 020 directions perpendicular to 020 plane. Oh, here's 111. That's cool. See, it cuts at 1, 1, and 1. And the 111 direction cuts through the 111 plane, perpendicular. This is an interesting one. See the origin? The plane cuts through the origin. Now what do you do? What do? You move the origin. So you move it, because we don't know where the origin of the universe is. It's just a unit cell. It doesn't matter. So we'll move the origin up here, and now what do we have? We have 1, 1, and minus 1, and just as before, we put 1 with a macron over it. That's 111 bar plane, and there's the 111 bar direction. It doesn't matter. It will always give you perpendicular. It's really cool. All right. And we can also specify a set of planes. So instead of using parentheses, we use brace brackets. And if we use brace brackets, we get families of planes. So for example, we could say if we wanted a particular face, so the face in the XY plane, face in the XY plane would be 001. right? Because it cuts the Z. So this is 001. But what if I wanted to say in a compact way all faces of the unit cell? All of the faces. So this is the particular plane. If I wanted to say all faces, I would write 001, but I can't use any of these containers, so I'll use brace brackets. So 001 in brace brackets means the whole set of 001, 001 bar, 010, 01 bar, 0100, and 1 bar 00. So there's only 6, and there's 6 faces. Again, mathematics imitating reality. What a concept. Make the math work for you. You don't work for the math. All right, and so just to make the point about the HKL plane is perpendicular to the HKL direction. So that's good. And the last thing I want to show you that comes out of the use of the Miller indices for planes is that another property that we'd like to know is the interplanar spacing. What's the spacing between like planes? So interplanar spacing, interplanar spacing. That is to say the distance between like planes. Distance between adjacent planes of identical index, adjacent planes of the same, I'm going to write it to be specific, the same Miller index. Same Miller index, HKL in parentheses. And the property that comes out of this, and you don't have to derive it, somebody worked this out for you about 150 years ago, is that the distance between adjacent planes with the index HKL is given by the ratio of A, which is the lattice constant. This is the cube edge, the lattice constant, that divided by the sum of the squares of H, K, and L taken to the power 1/2. So the square root of H squared plus K squared plus L squared divided into the lattice constant gives you the value of the spacing in between, and this is the A, just to be clear about it. So, for example, I think I've got some cartoons up here that show this. So here's 010. It's trivial. What's the distance here? This is just, the D010 is just A, right? How about here? This is 0 squared, 2 squared, 0 squared. This is D over 2. So this is an 020 plane, but if the distance between 020 planes is a half A, well then that's an 020 plane, then this is an 020 plane. So in point of fact, every 010 plane is an 020 plane, but every 020 plane isn't an 010 plane. You can see that some planes have multiple names. Here's another one. Look, this is the distance between adjacent 111 planes. It's A over root 3. So as the index goes up, as HKL goes up, the distance between successive planes goes down, and the angle between the planes goes up. The easiest one is orthogonal. Okay, that's good. That's good. All right, I think that's a good place to stop. I dread these kinds of lessons, and I'm sorry that the parents ended up here on a day like today, but there's a little bit of this kind of notation and taxonomy that they have to know, and so we suffer through it, and then we get on to the meat. All right, so now we're ready for some meat. So now that we can describe crystal structure, we're ready for physical measurement of crystal structure. So what I want to start today is the characterization of crystal structure by X-rays. Characterization. Characterization. How do we measure? I mean, how do we know that gold is FCC? We use X-rays. Characterization of atomic structure. Atomic structure by X-rays. By X-rays. And so today what I want to do is start, as I always do on a new unit, with a history lesson. We'll start with the discovery of X-rays, and we'll get into the underlying physics, and the next day we'll look at applications, including X-ray diffraction. So first of all, what are X-rays? What are X-rays? They're a form of electromagnetic radiation. They're a form of electromagnetic radiation. And they have the property that they have very short wavelength. Very short wavelength. How short? It's on the order of about angstrom. So strictly speaking, it goes from about 1/100th to 100 angstroms. So centered at about 1 angstrom is the center of the X region of the spectrum. And because they're a form of electromagnetic radiation, their energy is given by these equations, h nu, hc over lambda, or hc nu bar. Those equations that you've seen over and over again apply for the energy of an X-ray, because an X-ray is identical to a photon of wavelength somewhere down at this level. Why do we care about this? Because this is atomic dimensions. If I want to measure the dimension of the human hair, I don't use a yardstick. I use something that is of the human hair dimension. If we want to get into the characterization of atomic structure, we need a measurement tool that is on the order of that length scale, and that's why we're going to use X-rays. Now, other property, I said very, very short wavelength, but because of this inverse relationship between wavelength and energy, I want to draw attention to the superbly high value of energy. So let's plug in the energy for lambda equals 1 angstrom. When lambda equals 1 angstrom, we end up with 12,400 electron volts per photon. Per photon. Now, what's that mean? Just to put it in perspective, look up here at the table I've shown. We know that ionization energy, the electron, the lone electron in hydrogen is 13.6 electron volts, which is 14 to 2 significant figures. And then we go to helium, and these are, you pull these off the periodic table. This is the first ionization energy, and they're down around somewhere about 10 electron volts. Look at, this is 12,400. So let's go down to the 1 electron atoms. This is helium plus, this is lithium 2 plus, and we see a set of numbers here that follow this sequence, 1, 4, 9, 16, which is nothing more than the sequence you would expect for a series of 1 electron atoms. It's K, which is 13.6, times the square of Z. So Z here is 2, Z here is 3, Z here is 4, and so on. But even so, this is the last electron of nitrogen, the most tightly bound electron of nitrogen, 668 electron volts. That's a huge amount of energy, but it pales in comparison to 12,400 electron volts. So this is clearly ionizing radiation writ large. Ionizing radiation. What do I mean by ionizing radiation? It has the capacity to ionize everything. Every electron will be blown away. This is called knocking the stuffing out of the electronic structure. So that's what we're dealing with. So now let's go to the origin of X-rays. So how did we discover X-rays? Well, it was a dark and stormy night, not unlike the weather today, apropos of the lesson. It was November 8th, 1895. And it was at the home and laboratory of a professor. Of course it's a professor. Professor Willem Röntgen. Willem Röntgen. And he was a professor of physics at the University of Würzburg in Bavaria. University of Würzburg in what was then Bavaria, now part of Germany. And he was doing research, as many people were in the 1890s, on the properties of gas discharge tubes. He was studying gas discharge tubes. And he had a special interest in gas discharge tubes. Remember Lorentz, he liked to put the gas discharge tubes in a magnetic field, and Stark liked to put them in an electric field. And what was Röntgen's pet project? Röntgen loved high voltage. He loved high voltage and low pressure. He was focused on high voltage, low pressure, near vacuum. And so let's have a drawing of what he used. And here's an image of the museum that is literally in the house that was occupied by him. So the apparatus is sitting right there on the table. And here's the heart of the apparatus. I'm going to go to a fresh board because I need a little extra room here. So we know what the gas discharge tube looks like. It's a glass tube, sealed, and we've got feed-throughs for electrodes at both ends. Electrodes at both ends. And this goes down to a power supply. And the power supply that he used was batteries of chromic acid. And they were open beakers, and they were down in the basement, 2 floors below. And he had wires going from the basement up to the 2nd floor, and he was able to generate about 20 volts. So he had a number of these in series, because this is roughly a 1-volt system. So round numbers, he had about 2 dozen of these things in series. And I'm going to write here, in the cellar. In the cellar. Now, how did he get to high voltage? He put in here something that we would recognize today as an inductor. He called it a choke coil. A choke coil. And what the choke coil did is it would charge up until it got to 35,000 volts. And when it got to 35,000 volts, it would discharge and send a current at 35,000 volts to the cathode here. And with 35,000 volts, the cathode would send electrons boiling off the cathode, heading towards the anode with the kinetic energy associated with 35,000 volts. And this discharged at about 8 times a second. So I'm going to write 8 hertz here. So 8 times a second, this thing goes bam, 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 and the electrons go firing off here. And this, to make sure he had really low pressure, he had the cell open, actually, and this went to a vacuum pump. To a vacuum pump. So he had almost no gas molecules in here. Now, the way he did the experiment is he'd set this thing up, started it going, and this was after dinner. So on a Friday night after dinner, he's upstairs, and he wanted to measure emissions here. And so what he had, either get graduate students to sit there and you exploit their labor, or what you do is you put up a detector here, which was a screen. So this is either a sheet of paper or a sheet of cloth. So we call this a screen. It's a screen, and so you're going to look here. All right, you're looking at this, seeing what's coming out of this gas discharge tube, and it was a screen of paper or fabric, and it had been painted with a chemical that would glow if it were struck by a particle or by a photon of given energy. And they used, in this case, coated with the chemical barium platinocyanide. So cyanide 4 times. So barium platinocyanide. So you make an aqueous paste of this stuff and you gob it onto the screen. And when the screen is hit by something, it sparks. And the Latin word for spark is scintilla. Have you ever heard of someone being described as a scintillating conversationalist? It means they're sparkling conversationalists. So this is called a scintillation screen. A scintillation screen. And so presumably every time there's an event, the screen glows. And so Röntgen starts the experiment, and it's raining outside, there's thunder, there's lightning, there's a street light, as you can see right there, there's windows, and the thing is glowing, and he really can't detect what's going on here, so he decides to cover the tube. So he puts just a wooden box around the gas discharge tube. So now the gas discharge tube is enclosed in a box. And he continues the experiment, and what he sees is glowing on the scintillation screen. Scintillation screen is glowing, even though the gas discharge tube is in a box. There was another observation he made. The student earlier in the day who had painted the screen with the barium platinocyanide, I guess was practicing his calligraphy, and he left a paper towel on the edge of the bench, and he painted the letter A on the paper towel, and the paper towel was glowing with the letter A. And this thing is enclosed in a box. So he's saying, what's going on here? So he decides that there's some kind of an interaction between the screen and something going on in here. So he says, first thing he does is he says, well, maybe it's electromagnetic, maybe it's charged particles. So he takes a magnet and he moves the magnet around and nothing changes. He kills the power to the gas discharge tube, everything stops. So it's definitely inspired by 35,000 volt energy going into the tube. So then he says, okay, I'll take a piece of black paper. And he puts the black paper in between, and the screen continues to glow. So then he takes a book, and he puts the book in front, and he sees the shadow of the book. And he's standing here like this. He sees the shadow of the book, and he can see the shadow of the bones of his hand. So he says, you know, I don't think it's particles. I think it's radiation. I think it's radiation, and maybe it's something like that radiation that Hertz has been talking about. It's some kind of radiation, but I don't know exactly what it is. It's mysterious, and X is the letter of mystery. I'm going to call it X radiation. I'm going to call it X radiation. So he's discovered this mysterious form of radiation. Does he rush to publish? No. He's not going to risk his scientific career by announcing that he's discovered a form of radiation that can see inside the human body. That would be professional suicide. So he continues to repeat the experiments through November and December of 1895. And in January of 1896, he finally publishes, and it takes the world by storm. World by storm. By the way, how did he record this stuff? He used photographic plates. And he stored the photographic plates in his lab, in a wooden file cabinet. And so many of the plates were fogged, even before he got them to the experiment, because the X-rays, they were going everywhere in the lab. And he was working there the whole time. So what happens? What's the world reaction? January 16th, 1896, New York Times reports radiation that can see through matter and peer inside the human body. Peer inside the human body. You say, well, why is that? What's the big deal? Well, in London, immediately there was a market response. A manufacturer claimed to be a purveyor of X-ray proof ladies' undergarments. I mean, if you can see inside the human body, it's Victorian England. I mean, you know, how immodest can you be? This is a calamity. In France, of course, they don't care about such things. So they had a different response. Remember, this is where Daguerre invented halide photography. So there, it's very deep. It's very existential. Somebody claimed that with X-rays, he could irradiate and get a picture of the human soul. How French. But I'm sorry to say it, the wackiest comes from, guess where? The United States. No lesser an institution than the New York City College of Physicians and Surgeons. They proposed to use X-rays to project drawings from textbooks of anatomy onto the brains of students, thereby creating, and I quote, an enduring impression. In Iowa, we plumb new depths. There was a group out there claiming that they could turn copper pennies into gold. So this was the response. But you know, the thing that makes this so fantastic is, you know, we take it for granted that if I want to exercise power and exert a force on that can, I don't necessarily have to make physical contact with it. We accept this as given, that you can either have direct mechanical contact or indirect contact, magnetics, what have you. But in 1896, this wasn't given. So the notion that I could exert a force on something from a distance was very fresh. So it wasn't so easy. But there were benefits of the X radiation. Already in middle of 1896, there was a seamstress who had a broken needle in an industrial accident in Scotland, buried into her hand. A surgeon, I mean, this is trivial. Look, all you need is low pressure in a gas tube, and this, you could set this up in a high school. It's nothing. People had these set up in dentists' offices. It's nothing. So this surgeon was able to find where the needle was and then use precision to go in and take the needle out of the injured person's hand. In 1899, they were already using radiation in treatment of cancer. So what is the relevant physics? What's the relevant physics here? Let's look at the relevant physics. Well, when we're talking about 35,000 volts, and we're talking about energies in the vicinity of tens of thousands of electron volts, you know that this can't come from emission from an excited electron in a gas molecule. The gas binding energies are way lower than that. This must come from the solid. The electron leaves the cathode and it crashes into the anode. Here's the smoking gun. There's something going on here when the electron crashes into the anode and then gives rise to the radiation. So let's look inside the anode. Let's look inside the anode. So what's the energy level diagram? Let's say the anode is made of copper. So what's the energy level diagram look like? So we know up here we're going to have energy is 0, and the energy quantum state is infinity. Down here is the ground state, and the energy is the ground state energy. And we know this is up in the tens of thousands of electron volts. And then up here, there's an E2 for state 2. And up here is an E3, energy 3, maybe an E4 for energy 4, etc. And I'm going to write not to scale. This is just to give you a sense, not to scale. Okay. And so the ballistic electron with, in this case, 35,000 volts of energy comes crashing in to the anode, and this is one of these mixed metaphors. So this is a Cartesian drawing of an electron, all right? This is the incident electron, and its energy is given by the charge on the electron, which is E, and the plate voltage, which is 35,000. So it's got 35,000 electron volts, which turns into half mv squared. It goes crashing into this thing, and it's got enough energy. It can kick out top-level electrons, mid-level electrons, and in the extreme, it can eject ground state electrons in 1s. 1s. Oh, by the way, the spectroscopists, they don't like numbers. Remember, this is K, this is L, this is M, this is N. So we can eject K-shell electrons. What happens if we create a vacancy down here? All of these electrons above are unstable. If it's copper, there's 29 of them. Well, now there's 28 with a vacancy, and they fall down. And when they fall down from n equals 2 to n equals 1, there's a photon emitted. And that photon emission is in the X region of the spectrum. But we don't just get one wavelength. We get a plurality of wavelengths. N equals 2 to n equals 1, we get a photon. There's a possibility to go from n equals 3 to n equals 1. We'll get a photon of even higher energy or lower wavelength. Well, heck, if you've got enough energy to kick out an electron from n equals 1, you've certainly got enough energy to kick out an electron from n equals 2, so you could get a cascade from 3 to 2, which gives us a photon, or from 4 to 2, which gives us a photon. Can you see that you're going to get an entire set of lines? An entire set of lines. And we're going to label them because we don't have a single line. So what do we label them? We label them on the basis of the destination shell and how far they traveled. So this line here is known as the K alpha line. Why is it a K? K because that's the NF. That's the N number of the final state. And why is it alpha? Because the delta N equals 1. It came from one shell away. What's this one? It's got to be a K line because we ended at n equals 1, but the delta is 2. It went from n equals 3 to n equals 1, so this is called K beta. So there's a K beta line, K alpha line. This ends at n equals 2, which the spectroscopists call L. So we call this L. Delta is 1, L alpha. This is L, but delta is 2, so this is L beta. And what I can do is I could plot all of this on a curve showing the spectrum of this particular element. And what do I expect to see? I expect to see a spectrum that plots intensity versus some energy coordinate. It could be wavelength in this direction, which means that energy increases in that direction, and which has the highest energy. The highest energy up here is K beta, right? N equals 3 to n equals 1. So there's K beta. And then close to it is K alpha. And why do I put the K alpha line higher than the K beta line? I don't know what the relative amounts should be, but I suspect that if there's a vacancy, it's like musical chairs. If there's a vacancy in n equals 1, and an electron only has to go from n equals 2 versus n equals 3, the chances are the journey from n equals 2 to n equals 1 is easier and therefore more frequent than the journey from n equals 3, even though n equals 3 to 1 is greater energy. But 2 to 1 is more likely, and intensity reflects frequency. The wavelength reflects the energy. And then over here is L alpha, L beta. Now there's one more piece here. The precise value here is determined by the identity of the element in the anode. If it's copper, and I had to do this as a junior at the University of Toronto, I spent a whole year doing X-ray crystallography, and I will know on my deathbed the wavelength of copper K alpha radiation is, to 5 significant figures, 1.5418 angstroms. Now, if someone had fallen asleep in this lecture and opened their eyes right now and looked at the wavelength of this line as 1.5418 angstroms, and I erase the letter Cu, you take one look at that and you go, copper. Because only copper has a K alpha wavelength of 1.5418, which means I can use X-ray analysis to determine the identity of an unknown specimen. And furthermore, it's additive. So if I had a brass, which is copper and zinc, the zinc K alpha line is over here, and I will have both lines, and the relative intensities of the lines are related to the relative concentrations of the copper and zinc. So now I have a tool for chemical analysis. All of this from going upstairs after dinner and horsing around with a gas discharge tube. Okay, so we're going to end the formal lesson here, but we've got a few more minutes, so everybody's instructed to not make a lot of noise and just sit quietly. So let's take a look. This is an image. This is an image of Bertha. This is Röntgen's wife. This is her hand. He invited her into the lab, and she stood for a full 15 minutes in front of this tube, and in that 15 minutes got a lifetime's worth of radiation. But what we're looking at here, and what I'm going to point out to you in the last several minutes here, Röntgen was a prissy physicist, a really prissy guy. And he was German, which meant that the German academics had no contact with industry whatsoever. On the night of November 8, 1895, he invented 3 modern technologies. This is Bertha's hand. It represents the birth of medical radiography. Is there anybody in this auditorium who has never had an X-ray, dental or body X-ray? It's very rare. We see them all the time. We use them all the time. This morning I had one taken at about 9:10, right here, and I'm okay. All right. So that's radiography, medical radiography. Röntgen had a balance in his laboratory. One of the, the Justice, and she's got the torsion balance. So you put the unknown on one side, and then you put weights that are calibrated. These are made of brass, and they're in a wooden box. And so Röntgen had already covered the tube with a wooden box, so he took the emission from this and he radiated his box of weights. And what did he see? He saw dark regions where the weights were, because metals have a different electron density because they've got a greater atom density than wood. Wood is a more open structure, and so by contrast he could see inside the box. This is the basis for airport security. Röntgen had a gun. He was not holding up convenience stores. He was a hunter. He went into the woods, and he X-rayed the gun. Now, why did he X-ray the gun? Now, the gun is made of steel, but deep inside the steel there could be a flaw. There could be a crack. There could be a blowhole. The surface of the steel looks beautiful, but inside is a crack, and that crack could lead to failure under pressure. So Röntgen irradiates, and we already know from this that different electron densities give different shading, which means if there were a crack right here, you might see it in the radiograph. And this we use for certification of pressure vessels today. Certain pressure vessels that have to be welded have a specification that requires that every inch of the weld be inspected by radiation to be certain that there are no cracks deep inside the weld that under high pressure could open up, have an explosion, and cause injury, or in the worst case, death. So what's the outcome of it all? In 1901, when the Nobel Prizes were offered for the first time, Röntgen, by unanimous vote of the selection committee, was the first recipient of the Nobel Prize in Physics. So on that occasion, he was invited to come from Würzburg and to deliver a lecture in Stockholm. I've been to the place. It's a spectacular hall, gilded, beautiful champagne reception, elegant dinner, and he gives a lecture. And what's his lecture on? The discovery of X-rays. He received a huge amount of money at the time in prize money, and he returned to Würzburg. What did he do with the prize money? He donated it to the university to be used for scholarships for students studying physics. And to this day, students who study physics at the University of Würzburg are beneficiaries of the generosity of the first winner of the Nobel Prize in Physics. Such was his humanity. I hope you have a great weekend. We'll see the students back here on Monday.